Okay, chapter 2, we're going to talk about motion. This is kind of a broad learning goal, but you're going to learn various properties of motion. First off, a motion diagram is a series of images showing the positions of an object as it moves through time and space. So, here's an example of a motion diagram of a ball rolling off a table. It's nice because you can see the actual location of the ball, like snapshots in time, if these are equal time intervals of a like a strobe light, for example. And what you'll notice is that you can separate the motion diagram in the horizontal component and the horizontal component and the vertical component. And you can see that the ball is accelerating downward because it's gaining distance in equal intervals of time. And over here, in the horizontal, it's constant velocity because these equal snapshots of time reveal equal distance. So they can be very useful. We're going to use them to help us solve problems. Particle model simply replaces an object with a point. Okay, and we can also put a coordinate system on here and use some math and some formulas and functions to solve these problems. Okay, we need to know two things, vectors and scalars. We need to know what the difference between them is. Vectors are quantities that have both magnitude and direction. Okay?
I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude.
Okay, hopefully that helps you remember what a vector is. A vector is something with both magnitude and direction. Okay, represented with an arrow, but there's two distinctions that we have to make. We have to have magnitude, we have to have direction. Okay, so some examples would be velocity, acceleration. Both those things are something we can describe with a direction. It can be going in a car can be traveling in a specific direction at 70 miles per hour. So it's got both a magnitude and a direction. Okay, scalars are quantities that have only magnitude. For example, temperature and time. It does us no good to talk about the direction of time because it only has one direction. But we can give time a scalar value of magnitude for the amount of time that passes. Okay, some motion diagrams with vectors here. I've got a motion diagram here and then vectors drawn to the left or to the right of it to correlate with the motion. This is an acceleration vector here. So I've drawn these arrows to represent the acceleration at these instances of time. So let's say this is 1 second, this is 2 seconds, and 3 seconds, and so on. You'll notice that the acceleration is that this is a falling object. You'll notice that the acceleration downward is the same, and it's represented by all these arrows pointing in the same direction, and they're all the same length. So we're using this arrow to represent the acceleration of this object. It's always the same. In this case, it's always 9.8 meters per second squared. But the velocity changes. You'll see over here the velocity vectors that I have drawn here. They start off small, so you start off at 0 meters per second when you first drop an object or an object is first falling, but then it gains speed. It might gain to 4 meters per second squared, and then it might go 16 meters per second squared, right? So there's an acceleration, which means that there's going to be a change in velocity, and these velocity vectors are growing because the velocity is increasing. But they're all pointing down because of the same direction. The direction is not changing. Okay, here's another one for an object rolling off the table. Then I've taken the drawing above and I've put vector for velocity here, and I've split it up into horizontal and vertical components. So you can see the object's path goes like this, and what I've done is I've taken these vectors and slid them over to the object and slid these down. So you can see that the velocity in the horizontal direction doesn't change, represented by these vectors all being the same direction, same length. The velocity downward, however, does change because it's accelerating downward, so the object is going to gain speed. So by breaking this down into its components, these green vectors then represent the overall velocity vector of the object. And you can see what happens is the object's gaining speed in the vertical direction. So as time goes on, this vector is getting bigger, while the horizontal vector is staying the same. So eventually, this thing is going to be going basically straight down. You'll never be actually going 100% straight down, theoretically. But you can see that this vector is getting larger, so it is changing direction. This angle right here, this angle, I'll call it theta, is decreasing. And the object is accelerating downward. So it is helpful to be able to break an object into its horizontal and vertical components. Okay. Let's look at adding and subtracting vectors. Obviously, if the vectors are in the same direction, it's very easy. The resultant vector between these two vectors is just 7 meters per second. Downward. Take the bigger one minus the smaller one. To add or subtract vectors, you can take a vector and you can place it tail to tip. So I can put this vector over here, tail to tip, and you subtract them, what you have left over is 7 meters per second. Okay? It's a little harder if they're at different angles, so let's do perpendicular here. Once again, we can take the vector and place it tail to tip. The book calls this the parallelogram rule, I believe. So if you take this vector and place it down here, and take this other vector and place it over here, then you've made a parallelogram, where the resultant is the diagonal of that parallelogram. And you might learn this in math class as well. So the resultant is this diagonal, and to find it, we're going to use the Pythagorean theorem since this is a right triangle. Okay? It's 100 miles per hour here. Same as the opposite. So we're going to do a squared plus b squared equals c squared, so that's 100 squared plus 500 squared equals the resultant. I'll use the resultant squared here. And that'll give us our overall magnitude. In this case, that gives us 509.9, and that's miles per hour. That's our magnitude. So that's their overall speed. An example of this could be, let's say we have a plane that's flying at 500 miles per hour this direction and experiences a crosswind at 90 degrees of 100 miles per hour. The overall resultant speed of the plane is now, the plane's going to basically gain about 10 miles per hour in speed relative to the ground. And it's also going to change angles. So it's going to change directions as well. And we can find that direction by doing inverse tangent. So if we did the tangent of this angle theta equals opposite over hypotenuse, that'd be 100 over 500. We could get the new angle that it's going relative to the old angle, which in this case, if you do inverse tangent, you get, and I'm going to do this in degrees, not radians, 11.3 approximately degrees. So we changed directions by 11.3 degrees, and we gained about 10 miles per hour. Okay, they can get even more difficult, like if I give you one at a specific angle here, not a 90-degree angle. We do the same thing. So we're still going to use the parallelogram rule. I'm going to draw in this vector, I'm going to put it down here, make a parallelogram, take this vector and put it here, and the resultant is the diagonal of this parallelogram. Now, what's tricky about this one is there's not a good way to do this. This is a non-right triangle. Now, I could use the law of cosines, would be one way to do it because I have this side. But I don't know this angle as of right now. So there's different ways to do this. I guess one way you could do it is you could take this vector right here and you could break it up and do its vector projection along this way, and it's in the perpendicular. So you can break this vector into what's called its components. I can call this the x component and the y component, or vice versa. Call this the x and this the y. Then you can take those components and add them to this vector right here. So you would add the y to this overall magnitude and then add the x, and you make a new triangle essentially. And then so you place this here, and you place this here. And then you make this new big triangle, this new red one right here, and you can find the resultant. That's one way to do it. I'll just use the law of cosines for now. The law of cosines is c squared equals a squared plus b squared minus 2ab cosine of angle C, where angle C is, we're going to use this big angle. So we'll call this angle C and this side C. Okay. Now I can find angle C because this was a 45-degree angle, and since I made a parallelogram, one of the properties of parallelograms that you learned in math class was that this angle here and this angle here are supplementary. They have to 180 degrees. So this is a 135-degree angle. So that's going to go in for angle C right here, 135. We have minus 2AB. Now A is this side, and B is this side. We know this is 100 miles per hour right here, because it's the same vector from up here. So we have 500 and 100, and for A and B. And that's the same here, 500 squared plus 100 squared. And that's going to be equal to our magnitude over here, c squared. Now I'm going to have to square root all of this. So you have c squared, c equals this. Here's my new magnitude. Seems complicated. Let me pull out my calculator. And you can enter this all into your calculator fairly easy with the TI-84. Square root of 500 squared plus 100 squared minus 2 times 500 times 100 times the cosine of 135. Make sure you're in degrees. It should give us our answer of 575.1, I'll round to. 575.1, and that's miles per hour. So that's our resultant speed, 575.1. Now I'm going to use, we want to find the magnitude and direction. So we found the magnitude. The vectors have a direction as well, so we need to find this new angle right here that it's moved over because of this other force, this other wind, or whatever it is, pushing this object. So let's do the law of sines, I guess, because the law of sines works pretty well for all this. Sine of A over A equals sine of B over B. And it doesn't matter what variables you use. If you remember this from math class, we'll do sine of C over C, the extended proportion for the law of sines. Now we'll call this A, and we'll call this C. So the side sine of A, that angle. I'm sorry, this doesn't work because we don't know this angle up here, right here. We're trying to find. We know this angle, but we don't know these other two, so we can't use the law of sines. Sorry about that. Let me back up here. Let's erase this and a couple other things. All right, what I'm going to do is I'm going to split up this right here. I'll do this in green. I'm going to break this vector into its components. Those are it's a 90-degree angle. This is what is 100 miles per hour because it was the magnitude of this vector, which is the same. Let's see. I know this is a 45-degree angle, so I can use cosine to find this, and I can use sine to find this. So the cosine 45 equals adjacent, which we'll call x, and we'll call this y, is adjacent over hypotenuse. Multiply both sides by 100. You get 70.7, and that's miles per hour. And then for y, you do sine 45 equals y over 100, which also gives you 70.7. Makes sense, it's a special right triangle, isosceles right triangle. And so now we can do the Pythagorean theorem to find the magnitude, which we already have. So this is the other way to do it. And then we can also find this angle by doing inverse tangent of 70.7 over the 500 plus the 70.7. So that would be tangent of theta equals opposite, 70.7 over adjacent. So I'm looking at this big triangle right here. Which should be 570.7. If you do inverse tangent of that, you get your angle is approximately 7.1 degrees. So this is about, change direction about 7.1 degrees. We gained about 75 miles per hour. So we have our magnitude and direction.